Okay. Okay, hello everybody. So today, what question I'll be discussing is validating a binary search tree. So for that, I would like to first show you this. So what this actually means. So here we are going to validate a tree. Like here we are having an example tree that is 7, 4, 11. So what we actually want is that to validate that whether the element on the left of the root element is should be smaller than the node, and the element on its right side should be greater than the node element. So how we are going to proceed for that? So for that, here I am having 7 as my node element, so which I am denoting as root. I'll have a min value in starting as null, and I'll have a max value, that too I'll be taking as null. So after doing that, what I'm basically going to do is that if a root element is equal to null, that would be an edge case that we'll return a true that the given tree is a binary tree. But if this is not the case, then what we actually have to do is that we have to just check, go to its left element and right element and check for that element, that whether that element is less than the node element or greater than the node element. So first solution which I'm going to discuss is a recursive solution, that if this 7 is not null, then what we'll do is we'll move down to 4, compare it with 7. So if this 4 is less than equal to 7, then what we are going to return is that is false, because this would make the binary tree invalid. Same is the case with the right hand side of the tree, that if that 11 comes out to be sorry, here I was wrong, it should be greater than. If it is 4 is greater than 7, then I am going to make it false, and the else case would be that the element is true, and we'll move down further to the next two elements. So let's move down to this first recursive code for this. So first of all, as we discussed, this is a recursive solution, so I need to make a separate function for that. That is public. So what this would be returning is again a boolean. Let us name this is valid. So what we are going to pass in this is the root element, min value, and max value. That is and min.
Guys, is everybody clear about the algorithm? Does anybody has questions over there? Sorry, interrupting you, Ashmin. Just one minute.
Then int max. So these are going to be inputs or parameters for our function that we're going to use. So first condition, as I told you, is that if our root element is null, equal to null, then what we are going to do is return true. So second condition, what is that? Our root element is not null, and its left should be less than that. So if a root element is not equal to null, and then roots left, if roots left is greater than or equal to root, sorry, the roots value here is greater than the min value, then what we are going to do is return false for that. All right, and same would be the case with second part, that is if it's greater than max, again we'll be returning false. So these are the three cases For first case, we'll be returning true if the root is null, and second both are for just returning a false element, that whenever that root's value is greater than the main value, that is minimum possible value, and third case is that whenever the root's value is greater than the max value, then we have to return the false. So what basically will be min and max, that will be returning recursively in our function. So we'll call this function as, then we'll move this function to both its root elements. So as we saw here, first of all, we have made this point for 7. So whenever we have checked these values, that 7 if main value is null, then we are not going to check for second and third condition. That is, that whenever root element is not null, then only we are going to check the second and third conditions. Oh, sorry, I was wrong here. It should be min, and here it should be max. So whenever min and max is not null, then we are not going to compare this at all. Okay, so in the first case, 7 won't be compared with min and max. So when we'll move to next 4 and 7, then in case of 4, we'll making them for 4, this max value has to be 7. That 4 should be less than 7, and min will still remain null. And same is the case for 11. For 11, let me erase this a bit.
So Ashmit, we are not able to see where are you writing 4 and 7 and 11. And another thing is in line 17 and 18, both root dot value is getting greater than or equal to min and max. Is that the correct way?
I think that.
I'm not able to see my other screen, so let me check.
Yeah, so you were writing on the other screen and we were not. I think it's because of Zoom.
So let me check it if I am.
So you'll have to switch between the shares in both the screens.
Okay, yeah. So this is what I'm talking about.
Oh, now you need to explain everything because we were not able to understand from the first point itself.
Let me just make it clear. I was just explaining it all here. So I've taken an example of 7, 4, 2, 5, 6, and this all. Is it visible now?
Yes.
Starting what
awesome.
we're doing is that value of min and max we are taking as null. So in case of 7, when we'll be dealing with 7, the value of min and max would be null, and we won't be comparing min and max. We simply would be checking if the root element is present or not. If it is not present, we are just returning a true value. But if it is present, then we'll recursively move to the second and third element, that is roots left, that is 4, and roots right, that is 11. So now what we are going to do is next is that for 4, in case of 4, we are going to make its max value equal to 7, and its min value still remains null. Same is the case for 11. For 11, we are making its max value equal to still the previous value, that is null. My writing is horrible here. And main value will change to its root element, that is 7. So this would be happening recursively, like that is the case of 4 and 11. So from 4 we'll further move to 2 and 5. So we'll update the min and max value, that for 2 the max value will change to the next root value, that is 4, and similarly for 5 the min value will be 4. So this is how we would be doing this. Is it clear for everybody?
So if you can write for 2 what are max and min values, then it will be much more clearer.
Yes, sir. Yeah. So that is, I'll just erase this and go for 2. So for 4, as we noted that max value was 7. So when we'll further move down to 2, that for 4 the main value was already null. So for 2 again, there is no element on its left side, so its min still remains null, And for this, max would be updated to the next, that was previous root element, that is 4. What this actually means is that all the elements on left side of 4 has to be less than the max value. That is, all the elements on left side of the 4 has to be less than 4, and all the elements on right side of 4 has to be greater than 4. So that for 5, the min value will be updated to 4. Just to ensure that all the values on right side of 4, that is this side, has to be greater than 4. Like here 5 is greater than 4 or 6 is greater than 4. Similarly for 6, this value will be updated to 5. So if we are having some element on this side, here it's not possible. If in any case it's element over here, that for that its min value will be 5, so that this all elements are smaller than this value. Is everyone getting this?
What will be the max value in case of 5?
7, I think.
Here, that
For
remains
5,
max value, whichever it was for 4.
Okay.
If there is no value present, min or max for the current element, then it would be taken of the older value. We won't be updating that value. This all is happening recursively in our code.
Awesome.
So these are the 3 conditions. Now we have just to call the our function. So what we basically are passing is
I think you'll need to switch the screen again to lead code.
Yeah, sure.
In Zoom.
So,
yes, awesome.
So now I'm on my code. So from here we'll just be going to left of our element. So for left, we are updating the min value, that is min remains the same and our max changes to root dot value. Is it okay? And we'll be ending this with the right side of the value, that is valid. Here again, I'll be moving to root dot right and min, here will be updating the min, that is root dot value, max remains the same as it was in earlier case. So is it all right? So why we are basically ending this result and returning this? This is all because if we encounter with any of the false statement at any point in our tree, the whole returning element would go false, and here finally when we will call this element, that is return is valid, will be passing root, comma, null, comma, null. So whatever the final results comes out of this function, that will automatically be false if at any point in the tree this encounters a false statement, which means that the value of the element on left side is greater than min, or if value on right side becomes greater than max, then it will automatically return false at any one point, and our overall result will result into a false statement, and that will finally result a false value. So let's try to run this code. We are having some error at line 12. Oh, sorry. So null is not acceptable. It should work. Line 17. Oh shit. 2. So this works for our test case. Let's try to submit it.
Actually, it's failing for 213.
Yeah.
Check it once again. These conditions might be. If root's value should be greater than. Oh, here I'm wrong. This is the case for less, and this is the case for greater than. Yeah, if its value comes out to be less than min, It's need to be false. Yeah. Yeah, it's successful. Is it clear for everybody that how this all is running? If anybody has doubt, you can ask.
It became much more clearer when you did that in Paint
Yeah.
drawing. We were missing a lot of action. Neither.
So I have one more solution for this that is not recursive in nature. So that I'll again show you on Paint that how that works.
So me and Ashmeet actually discussed this problem yesterday, and we discussed about the binary solution. The recursive solution. But a lot of times the interviewer asks for, we don't like recursion. Can you do iteratively? So Ashmeet is going to present the iterative solution.
So what we'll be doing in our second solution, we'll be using stacks, and we'll try to compute in order for this binary tree. So if the in order is totally in ascending order, then the given tree is valid, else will return the false value that the tree is not valid. So what would be the in order for this? That obviously in order is always an ascending order if the tree is valid. So how in order works is, first of all, leftmost element, then node, then right element. So in this case, 7's left 4, 4's left 2. First comes 2, then we'll move on to its node, that is 4. Right side element is 5. We'll check it. If something is present on 5's left, then we'll write that, else we'll go to 5, then its right element 6. Then we'll travel back to 5, travel back to 4, move to 4's node, that is 7, move to its right, that is 11. So this is what we get its in order. If this in order is in ascending order, then the tree is a valid binary search tree, or else it's not a valid binary tree. So how we are going to compute this in order using stacks? Let's do that. Yeah, let me just make this tree again. So we were having 7, 4, 2, 5, and 11. Let's look for this. So first of all, we'll take a stack. So what we'll be doing in this stack is that we'll just pick up the first element. If its left is present, we'll keep on pushing this in stack, and whenever left element comes out to be null, that is in case of 2, then we'll pop and move to its previous element's right position. So how this would be happening? First of all, we'll move to it. This is the root element. We'll have a pointer named current, and we'll locate it to the root. So first of all, we'll pick 7, push it in stack. So 7 comes here. We'll check if left side is present for this element. So left is present for this element, that is 4. We'll push again this element over here. Then we'll again check its left is present. Again it's present. We'll take 2. So for 2, there is no element on its left side. So what we'll do is of this element, and we'll have a list of integers, so that from where we can check whether the given order is ascending or not. So in this case, we'll be appending this element in this list. So the first element in this list comes out to be 2. So first element is 2. So now 2 is out of this. So whenever we append this element, so what would be our next step is, we'll check that if its previous node is having something on its right or not. So in this case, there would be a pointer current that would be always behind the pointer which we are checking. So here current pointer would be pointing at this 4. So we'll move to current's right, that is current dot right. So current's right is 5. First of all, we have to append this 4. We'll append the current 4 comes out. Then we'll push the element on its right side, that is 5. If something further is present on both its left and right side, then what we would be doing is that first of all check its left side. If it's present, we'll keep on pushing on the stack, else we'll move back. So for 5, again there is nothing present on its left, then we'll append the current element and move to its right. So 5 will push 5, its right is again empty, so our pointer is moves back to 7 and append that 7. So this comes out, 5 comes out, there is nothing on its right, then 7 comes out too, and we push 7 in our list. So as I told, whenever we push the current element in the list, then we move to its right side, that is 11. So 11 comes into the stack, 11's left is null and its right both is null. So we pop this element 11 from the stack, and this is appended to our list, that is 11. So whenever this stack becomes empty at the end, so this means our in order is computed and we are having 2, 4, 5, 7, 11 as our in order. So next simply we can check that if this order is in ascending order, then our tree is a valid binary tree, else it's not a valid binary tree. Is it clear for everybody? Or any doubts?
Can't we check the validity inside in the in order array right then and there when we are pushing it? For example, whenever 4 is pushed, if we check whether 4 is greater than 2 or not. If it is not, then
it could be done while just appending. So just to make it clear, I was explaining that we will check it later.
Okay.
It could be done at any step. So let's move down to code. So here we'll be writing a second code for that. So first of all, we need a function to compute in order using stacks. So let's make that public. So what it would be returning is it would be just appending some element in a list. It need not return anything. So I'll make it a void function, that is public void in order. What we are going to need parameters in it. First of all, the root element of the tree, root, and second we are going to need is the list. This list I'll be using for appending the elements that we are taking out of our stack. So first condition, as it was in last algorithm, we'll be just checking that if root element is equal to null, there is no need to further check any element. We'll just simply return from this function. So if root is not null, what we are going to do? So first of all, let's create a stack which we are going to use for this. So stack will be having nodes in it. So stack of type, let's name this stack as well. New stack of type tree node. So now we have initialized a stack. We have condition for true. So what is our next step? That we'll assign a new variable of tree node type that will point to the root element. That is tree node. There would be which will always point to root of the node. So at the first point, that root and current both pointers would be pointing at the same position, that is top of the tree, that is root of the tree. There's something in chat. tree node capital N line 17.
जो मिशन बुझो मेरी
हाँ जी
मिशन ये ऑन ही है अभी
so so let me check line 17. Somebody is saying yeah, here it will be capital N. Thanks for helping out. So now we are having a current element pointing at root element. So what will be doing next is while whenever the root element is not null, that current is not equal to null, or whenever the size of stack is greater than 1, or we can say that stack is not empty, that is stack dot size is greater than 0. So for these two conditions, we are going to run this while loop. So there is a or condition in this, that if any of these condition is true, we are going to run the loop. So there would be again a while loop that would be only if current is not equal to null. Current not equal to null. So what this condition says is that if current is not null, this condition is true, but size of stack need to be 0. So what we'll be doing in this is we'll push element which is stack dot push current element. So whichever the current element is there, if current is not null, we'll push that element to our stack, and we'll move the current to, so our current to currents left. So after pushing this element, what we are going to do is we need to pop the elements and append that to the list. So we'll update the current that will move from its left to the node, that is current is equal to stack dot pop. We are going to pop element. We are going to push that into our list. That is L, that list was named L, yeah. We are going to push list dot add whatever the current value we are having, current value, and we'll update the current to its right. So I guess it's all right. So what is happening here again? Let's check it once again. If current is not null, or the size of stack is greater than 0, or our stack is not empty, we are going to enter a loop. In loop, what we are going to do, if current is null, then we are just going to pop the elements, which means that if we have reached the extreme left of our binary tree, then we are just going to pop element and append that into a list and move to currents right. But if that current element is not null, that we are having something at that point, then we are simply going to push that element into our stack and move current to the left. So I can't share both the screens at the same time. Let me just show you once again how this all is happening. Share. So what was happening is that first while loop is checking that our stack should be not empty, and the current pointer that was initially at this point, this should not be null. If this stack pointer is not null, then we are going to push that element into our stack and move to its left. That is happening in the first while loop. And if this condition is not true, that is current element is null, which means that we have reached this point, then we are going to this point that whose left is null, then we are simply going to pop out the elements to our list and append that into a list. So this is what is happening in our code. So let's move back to code. So I have made the function for in order. So now we are going to need a list and we need to check how that all works. So let's create a list of type teacher. We have named it as array list teacher. So we have created a list. Now we'll call a function which is named in order. Root, this we have passed both the parameters as required. So now next what we are going to do. So now we have all the elements appended in the list. So now we can either compare those elements here in this function, or we can simply compare it in this function, whichever the last appended element was there. If that element is less than the next element, then it is an ascending order and we can return true. And if that condition is not true, we can return false. So first let us make that, try that here. Let us first initialize. We take a loop that is for int I is equal to 0. I less than length of list So now let's check that the current element should be always less than the next element. If so, how we get elements from the list is L dot get I. We are having ith element. If L dot get I, if this element is greater than L dot I plus 1, what we'll do is L dot get I plus 1. So for this case, we'll return false. So if the previous element is greater than the next element, then we are going to return false. Else, if it comes out of this loop, we just need to return true value for that. So this, I guess it should again work well. Increase this length because we are going to access I plus 1 element. So if I'll keep the length complete, then it may go out of bounds. So let's make that L dot length minus 1. I guess it's all right now. Let's try to run this code.
Hey,
Ashmit, line 32, current is equal to current dot, right? And there is a dot at line 28, extra dot.
Oh, sorry, here I have an extra dot. Current.
no, at line 28.
28 as well. Yep. After current.
Yeah.
Could you scroll up, please? Look at line number 12.
Yeah, array list diamonds.
Oh, sorry.
There's gonna be
Yeah.
diamond, and you don't need to specify it on the right side.
Yeah, this integer is not required, but it would work in both cases. What's the problem here again?
The method is L dot size, not L dot length.
Yeah, that's sorry. Thanks for helping. Yeah. Would it work fine again? It's all right.
Hello.
So there is a problem with stack also, stack dot size.
It's a method.
So
Yep.
And line 23, N capital in tree node.
tree node. Yeah.
Yeah.
Now it is fine.
Yeah.
Could you go to line 16 as well? There's a semicolon after if.
Yep.
Oh, thanks. There's a lot of syntax error this time.
That's fine. That's fine.
It will work. Yeah, it works. So let's try to submit this code. We need an equal to condition somewhere. Need to remove the equal to condition. Let me check it. Yeah, here we need an equal to, because we don't need any duplicate elements in our tree. So if there are duplicate elements, we are going to return false. Yeah, it works. So
Awesome. So what we can do is, for the next problem, Ashmeet, we can record the problem itself in the meeting room, and we'll put that on YouTube.
yeah,
We will notify everybody. A lot of time today happened. I took a lot of time. All right, guys. Ashmeet, do you have anything? Sorry.
if anybody has any doubts, you can just ask.
Yeah, Ashmit, I just wanted to know, like, when you heard of iterative solution, when you said I want to do it iteratively,
Yeah.
how did stack came in your mind?
It came in my mind that there was this in my mind that for any BST, the in order is always in ascending order. This could be done recursively. In order is found recursively. That is just a 2 to 3 lines code. But I just wanted to do it without a recursion method because I've already done
No,
recursion.
I think what he means to ask is how did you decide the data structure should be a stack and not a
Like,
queue or a linked list or something, right?
iterative means, when I see iterative, I just think for loops, while loops. Then I wanted to learn, know the methodology behind why do you decided that, yeah, stack will be like, how to come you came to that.
No, if we need to solve, so in order, first I used to find the in order using recursively. So
Yeah, 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 yeah.
No. Ashmeet, let me take that question. I think I'm in a better position.
yeah,
So, Sarang, if you don't use stack, we can use linked list or a queue as well. If we are able to find whether the order is maintained, in order is maintained, that the increasing order is maintained. Let's take the case of queue. If we take queue and if we start finding out, comparing each and every element with the next one, what's the order going to be over there?
Mm,
O of n, right?
yeah, yeah, yeah.
So, for example, in stack, we with the last element with pop and push, it's an O of one operation, right?
Yeah, pop and push it.
But if we use queue or linked list, then what are you going to do?
Okay, insertion, deletion. Yeah, okay, okay, okay.
So that is one of the points, but it's not sacrosanct. We have to use a stack. You can very well use a linked list and a queue in this case. The code is going to get modified a bit, but we can
Got it,
use
got
other data structures. We just need to know what is the how expensive they are going to be.
yeah, yeah, yeah.
I
So
actually
that's the beauty of data structures and algorithms. Yeah, sorry, go ahead, Joshua.
I actually have one more solution using recursion that I'll be just sharing in the Slack. So you just see if you have any doubts, you can reach me for that. If you have any doubts in that solution.
Can we discuss the space and time complexity of the iterative solution?
Sure, you want to go ahead, Ashmeet?
So yeah, so in this, as it's we are using again this. Let me move to the paint. Mhm.
Ashmeet, actually, we are running out of time. If you can just tell the space and time complexity, I think people will be able to figure out pretty easily. Just बता दो इनको सबको कि time and space complexity. Yeah.
Yeah, so maximum space that we are using in a stack is that would be, I guess, O of m. Let me write it down here. Space complexity, order of n.
Correct.
We don't need more space than its height, because at a time there cannot be more elements than what is the total height of the stack. Okay, so and what is time complexity for this? So we are just having, there's a separate loop for just checking the ascending order, and there are a while loop or here that would be running for all the elements of H, and there's an element for normal that would be order of H square. That is,
No.
yeah,
So don't confuse it with the for loop that you are running for the in order.
yeah.
That is not the height. Actually, that is the number of elements in the whole tree one. Or wo parallel mein hai, right? So once we are completing the order of in order function, that is totally complete. After that, we are running that loop. So first loop, then the second loop. It's not running inside the loop. Okay.
Yeah, this
Ashmit,
I was just,
solution,
yeah,
the solution you posted 2 hours ago was of recursion.
yeah.
Okay, so it took double the time, almost same memory. I was seeing the
So
logistics.
that
Yeah,
that so quick question, Sarang. Let's stay there. Why does recursion take the extra memory? This question is going to be asked in the interviews.
Because
So
it's
yeah,
it's recursion, the function stack which comes on the
yeah.
no.
So it takes a memory on the stack. That's why a validate binary tree BST is they say that okay, do it iteratively also.
But it's
Everybody knows
just
that.
0.7 MB difference according to this.
That's fine. When there are thousands of data
Yeah,
moving out.
yeah.
Yeah, Ashmit, we can come back to the. Anybody wants to take a go at this one? That what is the time complexity of this algorithm? Prashant?
I am still not satisfied with the space complexity. How is it O of H and what is
We
H?
can come back to space complexity later. But what's the time complexity?
Okay. I mean, giving a cursory look, it should be order of n, because
Yes,
it's
it is.
not given that it's not given that it's balanced or not. So we
Okay.
cannot make any special comments on that.
Okay. Yes, we are hitting. Just look at this thing. If we go and look at the screen share presented by Ashmit, then we are hitting every node once. So it is apparently going to be off n.
Oh, fine.
But the space complexity is also going to be O of n, because stack is not the place which is getting which is taking more space. There is something else. There is one more data structure that we are using which is taking more.
The list L.
Yep, list L is taking more space.
Oh, sorry, I forgot about L.
Yep. But if it was stack only, I think Ashmit was going on the right direction when he was talking about the stack.
Okay, just
I
with
think we can do it. We'll try to explore it, and I think we can do it without the list. Can we do without the list? We can just keep checking in the in order itself that the new element which is
Yeah,
coming
we can
inside.
have a separate variable for that keeps
Yeah.
the previous element and we just compare.
Yep.
Yeah.
That
So
was
we can
Jaswinder,
save. Yep. Go ahead.
can we even talk about the height of the tree of a BST if it's not given that it's balanced? Because in the worst case, it's gonna be n, right?
yeah.
So we in the time complexity or space complexity, we shouldn't include O of H parameter at all, right?
That is, I want. You are thinking on the right terms, but I don't think so. That even if it is not a balanced binary set tree, I'll explore that comment and I'll fall back to you. That's a good question to ask.
When we give the time complexity, we're talking about the worst case, right? Big of O. So when it's not a balanced BST, it's gonna be O of.
The counter question is, the counter argument is that if it is not a balanced tree, then you are imagining a scenario that where all the nodes are lying towards the right of the BST or to the left of, right, in worst case
Yes.
scenario, है ना?
Yeah.
So in that case, the H is going to get transformed into N.
Yeah.
So it is still H, but it is equal to N. We can use O of H, especially there is a question that how do you find the height of the binary search tree. There are a lot of binary tree questions in which we take O of H rather than O of N. So we can use.
So Jacinda, just wanted to make a small comment, sir. Like in these interview kind of setup, first of all, when you are done with such kind of problems, then they ask you about the time complexity in binary tree cases. You will say that okay, this is O of H, that's the H is the height of the tree. Then they will say what is the worst case time complexity. Then the similar answer will be given by someone like Prashant, that it will be O to the power N. Then they will ask, how do you tackle that? Then the answer will be, we will use balanced tree kind of data structure. In that case, if we are really concerned about tackling the worst case time complexity, and that occurs more often than average case.
That's an amazing comment. I think you summarized it very correctly. So, but quick point, we don't give the time complexity in the end when they ask. That is one of the mistakes that we do. उससे एक point कट जाता है. So whenever you have to give time complexity before writing any line of code, once you have explained all the algorithm. For example, on the whiteboard where Ashmeet was doing, whatever he was doing, he should have summarized his time and space complexity then and there. Please make it a point. We have a communication framework, especially for interviews. Please stick to that. A lot of times people don't stick to that and they keep losing their points in the interview. It has taken a lot of data points to reach that communication framework. I have feedback from about more than 100 students. Where is that has been posted again and again in Slack. It's there on my LinkedIn. There is a blog on that how is the communication framework going to work. If you stick to that communication framework, force yourself, do the mock interviews, there is no way that you will not be making it to top 5. We have about 17 students making it to top 5 in last couple of months. So please stick to that. All right, guys. Thank you so much. Thank you. Ashmeet, do you have any comments?
No, it's all right.
All right. Thank you so much. And we'll be posting both the videos, what Ashmeet has covered and I have covered. I'll be making a new video. I could not record the first one. And Ashmeet will be doing one more video of the next problem. That is problem 38, 37 or 38, 37. And there is no session tomorrow. So have a great Saturday night. Go out partying and dancing. Bye.